function output is revealed. Now, what happens when these parties with inputs don't have enough compute power for this? Well, these days there are ways to outsource this job to other servers. These are special parties that don't have inputs but only help out in the computation, and the protocols ensure that no information is revealed to them. This is what we call MPC as a service. And today, with the blockchain boom, we have ready access to huge server pools that are online pretty much all the time. So the question becomes, how best can we leverage these resources to provide MPC as a service? Now, there is also a problem, and that is that this big pool sort of comes with a very powerful adversary that can control a set fraction of it. This may be a third or half of the server pool or even more. And worse, if this adversary is malicious, it can make the parties that it controls deviate arbitrarily from the protocol. So under these circumstances, we want a group of clients to avail MPC as a service from the server pool. This typically happens in a protocol where the clients send a message with their input somehow secretly encoded. Then the servers take over and they communicate with each other for as long as needed and send back messages to the clients that can locally decode the output. But the problem with this is that there are too many servers and they're already typically busy doing something else. So this makes such a protocol very inefficient if all the servers have to participate in the computation and communication. So ideally what we want is that the clients should send their message and a very small subset of this big pool does the computation. Now, however, what happens if the adversary can cause adaptive corruptions, meaning it can take control of the servers at will at any time in the protocol, and as long as the total number of corruptions is less than the allowed fraction. In this case, if the adversary knew the small set of servers that are computing, it can come and corrupt all of them. And MPC protocols are not secure when all participants are corrupt. So now the adversary knows the client's inputs, and this is very bad. So we need a way to address this efficiency versus adaptive security issue in large-scale MPC. And one way that this has been done is through ephemeral servers. That is, computation servers do not reveal their identities to anyone while they work, and this identity is only revealed once they communicate. The sort of philosophy here is that the adversary can't target and corrupt these parties before they know that these are the computation servers. This idea was first introduced in prior work as the YOSO model, short for You Only Speak Once. Today we'll see a slightly different model inspired by the same ideas that requires simpler setup. So here's an overview of what we'll cover. We'll first look into this ephemeral servers approach more, where I'll explain what the scales model is. Then as a start, we'll look at a semi-honest secure protocol in this model and talk about its building blocks. Finally, we'll discuss approaches to upgrade this semi-honest protocol to get malicious security. Okay, let's get started. So scales stands for small clients and large ephemeral servers. And as the name states, the model involves clients that provide inputs and do small computation. Their computation grows in the size of the security parameter, the function output, and the size of their private inputs only. It is independent of things like the function size, the number of other clients, the total server pool size, and so on. These clients need to speak twice, maybe thrice, and maintain states between messages. Then there are servers, and each server that participates in the protocol typically does work proportional to the function size. A scales protocol operates over a public append-only bulletin board and proceeds in a constant number of phases, like maybe 2 or 3. In each phase, first all the clients post one message to initiate the phase. Then for multiple rounds, one server gets secretly elected randomly and on the fly. So its identity as the computing party is unknown by anyone but the server itself. It reads the bulletin board, it does some computation, and then once it has created the message it needs to send out, the server first erases all of its internal state for the protocol. Then it posts a message revealing its identity. At this point, if the server was initially honest, it can now be targeted for corruption, and almost instantly. However, this does not help the adversary at all, since it has already erased all the state before posting the message. Then, In the next round, another such server is randomly elected, and so on until the end of the phase. And once this phase ends, the next phase starts and the same thing repeats. A scales protocol like this is secure when an adversary corrupts all but one client and all but one server in each phase. So how many servers are required per phase? Well, that really depends on how much of the server pool is corrupted. Say, if a fifth of the server pool was honest, then 1 in 5 servers in expectation would be honest on random election, right? So say 5 into some security parameter times more servers to be safe. So now notice two things. First, the number of servers and therefore the rounds have nothing to do with the function size. So all such protocols are constant round. Next, these protocols easily and automatically support dishonest majority server pools. And all of this with public communication only. There are no point-to-point channels. Everything is happening over the bulletin board. Okay, moving on, let's first look at the semi-honest scales protocol. And we build this using a special type of garbled circuits that we take from very recent prior work. But before we see what this special property is, let's quickly recall what garbling schemes are. This is a setting with a garbler and an evaluator, where for a function f with binary inputs of this form, there is a garbling algorithm that takes in this function and uses randomness to create a garbled circuit. It also produces this set of labels where there's a pair of labels for each input bit position in the function, a 0 label and a 1 label. From this set, if we take one label from each pair to represent the complete input x and the garbled circuit, and give it to the evaluator, this has an evaluation algorithm that processes these and derives the function output. Also, the garbling and the labels are such that nothing beyond the function output is revealed. So that was regular garbling done by one party. In the multi-party setting, we need security against all but one corruption. We need all the parties to participate in the garbling. And while distributed garbling exists, it requires a lot of interaction, which our communication pattern does not really allow. So we need a way to serialize this garbling process. And we do this by using re-randomizable garbling. So here, along with the garbler and the evaluator, there is this extra role of the re-randomizer. It can take a garbled circuit and add more randomness to it to create a re-randomized garbling, an RGC for short. This encodes the same function. It also outputs information that, when applied to the labels of the old GC, create labels compatible with the new GC. When an evaluator has this RGC and the new label set, it can again only derive the function output. Also, an extra security property that we need is that if a semi-honest adversary controls the evaluator and the garbler and sees all the prior randomness, the new RGC will look no different from a fresh garbling of the function. Now, this convenient tool already gives us a template to build a scales protocol. And the idea is to make the servers do the job of the garbler, the re-randomizer, and the evaluator. So we have a bulletin board and let there be two phases. One where we garble the circuit and the other where we evaluate the garbling. In the first phase, all the clients encode their inputs in their first message and post it. Then, well, we won't have the time to go into the details of it, but roughly this involves clever use of like 2-round OT, and this is the receiver message. Then the first server acts as the garbler and the OT sender. It garbles the function, creates the OT sender messages with the GC labels as inputs, and posts these. Then every other server acts as a re-randomizer and OT updater. It re-randomizes the latest GC and updates the latest OT sender message so that the labels in them match the new GC, and then these are posted. In the second phase, the client reads the last OT server message for their input bit only and posts the evaluation labels. Then a server evaluates the last GC. This protocol is semi-honest, secure, and it's secure when the adversary corrupts all the clients, the evaluator, and all but one server in the first phase. And this is our starting point from which we'll build our maliciously secure protocol. Okay, so what remains right now is to lift this to malicious security, and since we're in the dishonest majority setting, the best we can really hope for is security with abort. So, what we need to do for this is, well, two things. We had used an object for garbling and a protocol for OT. So, first of all, we switch out the semi honest OT protocol with a maliciously secure one. And we already have a problem. Our communication pattern needs a two-round OT, and two-round OT that is maliciously secure doesn't exist. Well, at least not in the plain model. It does exist in the random oracle and the CRS model. So we need to use one of them. But for our OT to be updatable, we need some special structure that the random oracle does not provide. So we settle with the CRS model, and for those who know, we use the PVW OT. Next, note that the garbling is secure only for honestly garbled circuits, so we need to force this honest behavior somehow. All our garbling related tasks are done by servers that can only speak once and never maintain state, so this puts us in a bind. One thing we can do is to make the servers prove in zero knowledge that they did their job right. And we already know that machinery for this exists, so now the servers can do their semi-honest tasks and be the prover in a ZK snark that posts a very succinct proof. And this is neat. This requires setup, like the CRS or the random oracle, and the proofs are short and publicly verifiable in real time. But this is non-black box in the garbling, and while garbling correctness is an NP statement, uh, it has a very large representation. So the prover that has to prove this has to do a lot of work, which brings us to the question of, sure, we have ephemeral servers that can do very large computation, but can we do better computation wise? So here's the solution that we propose, and that is again to use zero knowledge proofs. But this time it's not generic proofs. We use proofs that are black box in the RGS and sort of leverage its homomorphic properties to gain simplicity and efficiency. Okay, so here's a Sigma protocol for proving correctness of garbling. The proof is for correctness of re-randomizing is similar, and roughly both of these follow the same outline as the discrete log Sigma protocol. Recall that there was a prover and a verifier, and the prover samples some randomness to make a structured first message. The verifier samples a bit, and depending on this, the prover will either reveal randomness to show that the first message was honestly constructed, or it will use this randomness to mask the witness somehow so that the verifier can do an oblivious check. Similarly here, the prover has some randomness, and this is the witness, and it has to show that the GC was posted that was correctly garbled. And to do this, it samples more randomness and re-randomizes the GC. This RGC is sent to the verifier. And the verifier now samples a bit, and if this bit is 0, the prover opens the randomness to show that the RGC was a correct re-randomizing from GC. Otherwise, it opens some combined randomness to show that the RGC was a correct garbling from F. And that's all. This is a Sigma protocol with soundness half. Now there are a few details that I won't be going into, like what allows this randomness composition and how to make sure that the OT input labels are consistent with the garbling. But this is the high-level proof, and we make it work. If this protocol were used as it is with the semi-honest protocol, it gives us a covertly secure protocol with only double the semi-honest costs. For malicious security, though, we would need to amplify soundness using parallel repetitions. So with S repetitions, you get 2 to the power negative S soundness error. Okay. Given such Sigma protocols, we need to convert this into zero knowledge proofs that comply with our communication pattern, and we are done. So we need our prover to speak once. And one very obvious way of doing it is using the Fiat-Shamir transform. This roughly takes a 3-round Sigma protocol and converts it into just one publicly verifiable proof message that the prover sends the verifier. But this needs a random oracle, and we already use the CRS, so we would want to avoid using more setup. So here is another alternative approach that we present, and that is to again use a variant of OT. We call this the distributed committed index oblivious transfer, and this basically allows multiple receivers to non-interactively pick a random choice bit. Everyone picks a bit and encodes it, and then the sender's output revealed corresponds to the XOR of these bits only. We won't go into the details of its construction, but we can make this from 2-round OT. The protocol for this would allow for this bit to be committed before the sender's message. And now you can kind of see where we can use this in the zero knowledge proof. The idea is to make the clients do the receiver's job again and pick the verifier's random choice bit. Then the server, acting as the prover, creates the Sigma protocol first message and the third message for both choices of the bit. It creates the OT sender message with these as input and posts this with the first message. Then the clients post some public information each, and this can let anybody decode the OT output. We call this ephemeral prover zero knowledge, EPZK for short, since the prover needs to speak once. Okay, now we are ready to put all of these together to build a maliciously secure scales protocol. This will have 3 phases. First, in the encoding phase, the clients post the OT receiver message, encoding their inputs and also their contribution to the ZK challenge. Then the first server posts a garble circuit, OT sender messages, and the EPZK prover message. Every other encoding server re-randomizes the previous garbling, updates the OT messages, and posts its own EPZK prover message. Next, in a verification phase, the clients post information that allows everyone to complete the EPZK proofs. Then one by one, servers verify all the computation of the encoders and post accept or reject. If all these servers accept, then in the decoding phase, the clients post the input labels for the final garble circuit. And then a set of decoders evaluate the garbling and post the output. The clients believe them if they all post the same thing. And well, that's all. So this protocol is secure with a bot when the adversary corrupts all but one client and all but one server in each phase. So to summarize, first off, all the building blocks that we use can be constructed assuming DDH. And we just looked at how to make maliciously secure scales protocols and 2 ways of doing it. So one way is using the random oracle using fiat shamir, and this would require the clients to speak only twice. And the other way is the protocol that we just saw that had 3 phases. And these protocols are both universally composable. Looking ahead, here are some possible directions for future research. It still remains open, for instance, to design scales protocols that provide guaranteed output delivery in the honest majority setting. So public communication over a bulletin board only, and one randomly elected ephemeral server per protocol. Note that our protocol is in the honest majority setting still provides security with a bot. Another open problem is to design maliciously secure protocols in the plain model or even in the random oracle model, but without a CRS. And finally, it remains to see whether we can make scales protocols from other hardness assumptions. Thank you.
Kuma, Nama is gonna give the talk.
Am I audible? Am I audible now? Okay. Hi everyone. Okay, yeah. This is not working. Here we go. Yeah, hi everyone. This is our paper on 10-party sublinear secure computation from standard assumptions. I'm Naman Kumar, and this work is done in collaboration with Jafar Koteau. Yeah, I'm from Oregon State University. He's from IRIF. Okay, so everybody's wondering why 10-party sublinear secret computation. So let's get started and we'll see why this works. So just to remind ourselves, like, what's the motivation behind what we're doing today? MPC is, there are like multiple parties and they want to compute a function of their private inputs. And in particular, the MPC case that we're going to be dealing with is the general case. So we won't be looking at like specific protocols such as PSI or peer. We're considering the case in which there are like multiple parties and they have a common circuit and they want to compute a function of this circuit on their private inputs. And in particular, the question we're interested in is the communication complexity of general purpose MPC, and whether the communication complexity can be sublinear in the size of the circuit. So it's order of, so it's small o of C. For more details about the model that we're going to be working in, this is in the semi-honest setting with dishonest majority, static corruption models, and in particular, our work really deals with the multi-party setting. The circuit class, ideally, we want to deal with all circuits, right? P by poly. This is what we want sublinear MPC for. But for various reasons that I'm going to be describing throughout the protocol, we're going to be limited to layered circuits. Okay, so this is not the first work on sublinear MPC. In particular, there have been like several works in the past. So the easiest way to get it is using FHE, but of course, FHE is only limited from lattice assumptions. And although we can get it for like all P by poly, we want to be able to see if we can like do it from further like more assumptions. HSS is the second technique, which is homomorphic secret sharing. I'm going to be describing more about that on the next slide, but as you can see, we have HSS from more assumptions, and even though the amount of communication it's pretty high, it's still sublinear. And in particular, we also have HSS for a smaller family of circuits, which is like log and log depth circuits. Yeah, and the third technique to get sublinear MPC is using correlated SPIR, which is, the name sounds horrible, but I'm going to be describing this at the very end. And this is also from like more assumptions with like slightly less, but still sublinear communication. Okay, so what is homomorphic secret sharing? Well, this is basically a primitive in which there are like multiple parties and they want to compute a circuit on some input X. What they can do is they can run a shared generation protocol, which allows them to get HSS shares. So if we have two parties, Alice and Bob, they get X0 and X1. These are HSS shares, which have the privacy property that they hide what X actually is. And in particular, they can run an HSS evaluation algorithm. This evaluation algorithm is defined over a certain circuit class. And for any circuit within this circuit class, you can run the evaluation algorithm using your HSS shares in order to get additive shares of the output. The key idea here is that this is completely non-interactive. So once the shared generation technique is done, you can just non-interactively get additive shares. And in particular, you can like, reconstruct them. Okay. So there are a variety of ways to get homomorphic secret sharing. We have many, many constructions over the past 10 years. But the ones that I would like to draw your attention to is the second one, BGI16, which is from DDH. And it's for a class of programs known as RMS programs, which are restricted straight line multiplication programs that encapsulate branching programs and NC1 circuits. However, this does have an error probability, which as you can see is a 1 by poly, a polynomial correction error. The second scheme that is interesting is the DCR-based approach, which is the last one. This is all for RMS programs, but like using DCR and Peihan-based encryption, it is possible to get a negligible error. And the third scheme is this one, the one from LPN, which works for low-degree polynomials. So what I mean by low-degree polynomials is that if you have LPN, if you assume standard LPN, then you get it for constant degree polynomials. However, if you assume super polynomial LPN, do a little bit of complexity leveraging, then you're able to get it for log depth circuits. Yeah, so these are the three HSS schemes that we'll mostly be dealing with. And the important part here is what circuit class these work for. Okay, so how do we get sublinear MPC from HSS? Well, the protocol is extremely simple. All you have to do is two parties, they send Elgamal encryptions of their inputs to each other. And really, like this is, in fact, the shared generation algorithm. And after this, they can simply non-interactively evaluate their circuit using the HSS evaluation algorithm on these inputs, and they get additive shares of the output. So a few things here. First of all, if you will notice that if we have HSS for a certain circuit class, then the communication is completely independent of the size of the circuit. And in particular, HSS for a circuit class immediately implies sublinear MPC for that circuit class using the protocol that I just described. N-party HSS, furthermore, using the same technique, you can get N-party sublinear MPC, and the communication really only scales with the number of parties. So it does not scale with the size of the circuit at all. Take my word for this, but this also works for layered circuits. So we have HSS for log depth circuits and log depth circuits and so on. But if you have HSS for like any non-trivially deep circuit class, then you can automatically get it for layered circuits with a certain amount of well, not HSS, but sublinear MPC for layered circuits with like some amount of sublinearity. So what is our result? Well, before that, let's take a look at previous works. These are all these different sublinear MPC constructions. All of them are limited to 2 parties, except one work last year, which I think this is Eurocrypt of last year, in which they obtained from the assumptions DDH or DCR plus LPN, so one of DDH and DCR, they're able to obtain either 3-party or 5-party sublinear MPC. Our work is we increase the number of parties for which we know sublinear MPC, and we also furthermore increase the number of assumptions for which we have sublinear MPC. So lots and lots of results, but the one that I'd really like to draw your attention to is like the titular result at the end, which is assuming superpolynomial DCR DDH, one of them, and superpolynomial LPN, plus a low degree PRG. So what I mean by a low degree PRG is a PRG which is in the circuit class of constant degree polynomials, which can be constructed on many, many assumptions. So you can instantiate it from Goldreich's PRG, you can instantiate it from the one-wayness of random local functions, and you can also instantiate it from multivariate quadratic. Yeah, using this, you can get sublinear MPC for layered circuits with communication of order of S by log, log, log S. So it's a very, very small, a very tiny amount of sublinearity, but it is sublinear nevertheless. And this works for 10 parties. Okay, so there is some concurrent work that I would like to describe here. So last year's crypto, there was a work by Dao, Shai, Jen, and Lin, in which they get n-party HSS from sparse LPN. This is an assumption in which the public matrix of LPN is sparse. And using this, they can get n-party sublinear MPC for layered circuits with S by log log S communication. Unfortunately, this construction does have a inverse polynomial amount of error. However, in our paper, we show how to obtain sublinear MPC with perfect correctness using a correction technique that we introduce in our paper. This does not correct the HSS error, however. The second paper that is interesting is by Abraham, Roy, and Scholl, which is in this year's Eurocrypt, in which they get n-party sublinear MPC for layered circuits from DCR. However, they do not construct n-party HSS in order to do this. And yeah, this does have the characteristic that there's no error here. Okay, so how do we get multi-party HSS? Well, HSS for 2 parties is known. However, the main technique through which we can get HSS for multiple parties is by using this nesting technique. So how does this work? Well, assuming that you have an HSS for a circuit class, so let's say C, what you can do is you can use the share generation algorithm in order to generate HSS shares for the circuit. Furthermore, if you have an HSS for the evaluation algorithm of the HSS share on this circuit, you can actually like use this as the function as an input, and you can use HSS in order to share it a second time. So now you have like 2 HSS evaluation algorithms nested inside each other, and on evaluating them, you get like circuit outputs. You get like additive shares, right? And you know, additive shares of additive shares are additive shares, so you get additive shares of the circuit output. Yeah, we call these the inner and outer HSS scheme. Now, the evaluation algorithm for this to work needs to be an NC1, because remember, we only have HSS for NC1 circuits. And furthermore, in fact, in previous work, it has been shown that if the circuit is constant depth, like the underlying circuit which we want to compute is constant depth, then evaluation using DCR-based HSS and a low degree PRG is in fact in log depth. So you can nest it once in order to get 4-party HSS. So this does it work now? Okay, yeah. So our first contribution is nesting imperfect HSS. So the previous slide, the technique that I described in the previous slide works automatically for the DCR-based HSS. However, we show how to do it for the DDH-based HSS. So let's understand like what exactly is the bottleneck here and why we are not able to immediately use this technique for DDH-based HSS. The crucial underlying technique behind HSS is something known as the distributed discrete log algorithm. So what this does is basically if you have multiplicative shares of an input, then you can actually convert these to additive shares over the integers. So shares in the exponent can be converted to shares into the integers using this technique. So what you do is consider your group, which is basically a circle, and you have G0 and G1 as shares and multiplicative shares of the secret in the exponent. After that, you can like find a distinguished point. So you know, one way of like finding distinguished points on the group is simply by using a PRF. So if the PRF output on the group is something that is like, you know, starts with many zeros or something, then you can call it a distinguished point. And you can fine tune this probability in order to be able to ensure that a distinguished point is a certain amount of distance away from these multiplicative shares. After that, you can simply like walk across the group, multiplying by the generator, and at the end you reach this distinguished point and calculate the distance from this distinguished point. This distance is actually simply the sharing over the integers. Okay, so what we do show is how do we parallelize this effectively. And in order to do this, what we understand is that parties can actually like pre-compute the products of the generator, and then they can like evaluate all this in parallel. Furthermore, they can determine if a point is a distinguished point by running it over a low degree PRF, which we need it to be in NC1. So one way of getting a PRF in NC1 is to use a PRG in NC0. Then GGM simply gives you a PRF in NC1. And then you can like simply calculate the distance from this distinguished point using maybe a binary tree or something like that. So the whole technique can actually be put into NC1. Our second contribution is how to get 8-party HSS. So the way we get 8-party HSS is by using a different construction. So if you recall, I told you about a construction of HSS from LPN. And what this construction does, it starts with an n-party DPF. So a DPF is a distributed point function. So if you have a point function which evaluates to 1 on some point and a 0 on other points, then distributed point function is basically a way of generating 2 keys, which you can give to 2 different parties, such that these parties can evaluate this function on any input of their choice, and they get additive shares. So it's almost like a dual of homomorphic secret sharing, which it actually is. So DPFs crucially can be constructed using just one-way functions. In fact, like 2-party DPFs can be constructed using PRGs. And the transformation is actually very, very similar to the GGM transformation using which you can get a PRF. Now, the key idea here is that the complexity of the HSS.eval, which is the evaluation algorithm of the HSS, obtained through this LPN-based HSS, is actually just the complexity of the underlying DPF. So if we have a DPF which is in NC0, then we automatically get an HSS evaluation in NC0. And that's what we do. So as I said, this mimics the GGM construction. So we can actually just increase the branching factor of the GGM construction. And furthermore, if we use a PRG in NC0 for constructing our DPF, then we can get a constant depth distributed point function for polynomial domains, which suffices for our application. Okay, so now we have 2-party HSS in NC0, and we have HSS for NC0, which we can obtain from like DDH or DCR or whatever. You can actually like once you have the HSS shares, you can split them, and then you get HSS 4-party HSS with the evaluation algorithm in NC1, which you can further split because we again are able to do it because we have HSS for NC1, and this gives us 8-party HSS for low-degree polynomials. So the LPN-based construction, again, if you assume standard LPN, then you get it for constant degree polynomials. If you assume super polynomial LPN, complexity leveraging simply gives you for log-log depth circuits. Yeah, so these are the assumptions. Okay, so I don't know if I have enough time to describe the second part of our construction, which is how we get which is a technique to get from n-party HSS to n+2-party MPC. But the basic idea is we use this correlated SPIR technique. So what is SPIR? This is symmetric private information retrieval. And in particular, if you want to use this technique to get sublinear MPC, then it's really just as simple as one party has a truth table, and the other party simply queries the point of this truth table using private information retrieval. So this can be done using linearly homomorphic encryption in LPN. And this is, we can ignore that remark for now. But the idea is simply that if you have HSS for n parties, then this truth table that needs to be computed by one party can actually be computed in a distributed manner using HSS. So now they are able to share this these truth tables, and they all have additive shares of these truth table. And furthermore, like the n+1th party can now simply query using the previous correlated SPIR technique with every single one of the parties involved in the HSS, and it can obtain additive shares of the output. So this was described in last year's paper, and in particular, the total map communication that you get here, it also scales only with the number of parties and not with the size of the circuit. Okay. Our technique is very simple. We do exactly what we did the previous time. We use HSS. So now here, we do a lot of complexity leveraging, and we make some super polynomial assumptions. We reduce the size of the database to be queried even further until we arrive at the point where the evaluation algorithm, the receiver's algorithm in the peer scheme is in fact in NC1. So the query algorithms and the decode algorithms are in NC1, which means they can be split using HSS. And now we split it again. And in particular, now we get 2 parties which have HSS shares. And furthermore, they can use the evaluation algorithm to evaluate the HSS, to evaluate the correlated SPIR, get additive shares back. And again, once they broadcast the shares, this gives n+2-party MPC from n-party HSS. Okay, so let's put all of this together. So we have 8-party HSS for low-degree polynomials. We have we have our n to n+2 extension, And if you look at all the assumptions, then using superpolynomial, DDH, or DCR, one of them, plus superpolynomial LPN and a low degree PRG, we are able to obtain 10-party sublinear MPC with this horrible order of S by log S factor, which is still technically sublinear. And we have studied the complexity, communication complexity of multi-party computation. Okay, so that'll be all. If there are some open questions here, then it could be extending the number of parties for which you have HSS from 8 to arbitrarily many, or increasing the circuit, the circuits that we have sublinear MPC for. But these are all pretty well known open questions. Yeah, thank you.
Are there any questions from the audience? Right, if not, let's thank the speaker again. Okay, our next talk will be privacy preserving Dijkstra, which is using MPC to compute the Dijkstra's algorithm that computes the single source shortest path in a weighted directed graph. This is impressively a single author paper by Ben Ostrovsky, which is starting as a freshman at Caltech. And Ben is gonna give the talk.
Yay. Okay, hi, this is Privacy Preserving Dijkstra. This work was done while at Santa Monica High School, but now I'll be moving on to Caltech. So our setting is 2 or constant number of servers, honest but curious. All inputs and outputs are secret shared. And servers can talk to each other privately. So through MPC, servers can execute atomic secure operations on secret shared data, like add, multiply, compare, etc. And we count the number of rounds and the number of such atomic operations. And so our main question is, how do we process graphs obliviously? So the plan for right now is, first I'll talk about graph representations. Then I'll talk about the statement of our results. Then I'll discuss some of our techniques, and I'll end with conclusions. As you all know, one way to represent the graph is an adjacency list, which is more compact than adjacency matrix for graphs which are not dense. And here we have a graph where 1 points to 2 and 3, 2 points to 3, and 3 points to nothing. It's going to be like linked lists. And one way to store this securely is by hiding what is a vertex and what is an edge. So here we have one list where it consisting of secret shared 2 tuples, where the first element in each tuple is Boolean, 1 for vertex, 0 for edge. And the next element is the name of this vertex or edge. So for example, the first thing in this list is secret shared 1, 1, 1 indicating that this is a vertex and its name is 1. And then we have 0, 2, 0 indicating that this is an edge and the edge's name is 2, and so on. So this representation doesn't reveal the graph structure. And for Dijkstra, we're given this adjacency list also with secret shared weights for both vertices and edges. For vertices, it's like bots, so you can't tell the difference between the two, and secret shared start node, S. So when we do graph processing, we want to explore all the edges adjacent to some vertex. However, some vertices may have very high degree and others may have quite low degree. And so we want to hide the degree distribution in the graph. And the way we do this is through our so-called denormalized replicated adjacency list. So the idea here is to normalize the adjacency list of every node to be of exactly the same length D. Some nodes, like up the white one, have very high degree, and some nodes may have very low degree. And so for the nodes that have high degree, we'll chop it up into blocks of length D, where the last block may not even fill D completely. And then we'll treat each of these blocks as new adjacency lists. On the left, of course, we'll just replicate the same vertex, so these know that they belong to the same vertex. And then for all adjacency lists with degree less than D, we'll pad them with bots to exactly length D. And now when we compute Dijkstra, we can go to any node and take a block of D edges and explore all of these in parallel. And this doesn't reveal any information because every single adjacency list looks like this. And in the paper, we show that when we let D be twice the average degree and we provision 2V potentially replicated vertices, then any graph can be denormalized. So now the main question becomes, given a secret shared graph G, how do we convert it into a twice average degree normalized replicated adjacency list obliviously? In other words, how do we take a secret shared adjacency list and through an oblivious algorithm, massage it into a D by 2V table where each row in this table is D edges all belonging to the same vertex? Okay, so now I'll talk about some of our results. They're all of them. So our first result is exactly this. Given a secret shared graph G, we can convert it obliviously into a twice average degree normalized replicated adjacency list with O of V plus C log V secure operations and O of log V rounds. We show that if vertex names are integers from 1 to V and the adjacency list is sorted by vertex names, then we can obliviously convert it into a twice average degree normalized replicated adjacency list even quicker, and more specifically with linear work and constant rounds. We also show that for any adjacency list where the vertex names may be arbitrary alphanumeric labels, we can convert it into this nice adjacency list where vertices are integers 1 to V and sorted with V plus C log V secure operations and O of log V rounds. And if you're paying attention, then results 2 and 3 imply result 1. For Dijkstra, we also need oblivious priority queue. And so we start with the Jafar-Goli Larson-Simkin optimal oblivious priority queues from SOTA 2021. They work in the client-server model, and they show that there exists a client-server oblivious priority queue where each heap operation requires log n work, log n client memory, and log n rounds. Of course, there are no trusted clients in MPC, and so we build on their work. And assuming secret shared input, secret shared output, pseudorandom function, we show that there exists an MPC oblivious priority queue where each heap operation requires log n work and O of log n triple log n rounds. Additionally, our oblivious priority queue supports parallel insert of elements instead of inserting them one at a time. And jumping ahead, we'll insert D less than n elements into this oblivious priority queue in parallel with O of D log n work and O of log n triple log n rounds. Finally, assuming CISO-PRF, given a secret shared adjacency list for any weighted directed graph G with positive weights and start node S where everything including weights is secret shared, there exists an honest but curious to a constant number of servers MPC for Dijkstra with O of V plus C log V secure operations and V log V triple log V rounds. And this is an improvement over the state of the art. Okay. So now I'll talk about some of our techniques, and I'll start with computing the denormalized representation. Recall that as input, we're given the secret shared adjacency list, and there's a predicate that can tell vertices and edges apart. Now we want to know how to transform this adjacency list into a denormalized adjacency list obliviously. Well, first, we'll break it up into blocks of length D. And recall that since we know the number of vertices and edges, and D is simply twice the average degree, D is publicly known. So we can break it up into blocks, And then we can pad the last block to length d with bots as needed. And now observe that there's some spillover into the next blocks or block. So for example, the second and third block have the adjacency list spilled over from the previous block. And so we'll mark these spillover blocks for later with secret shared Boolean, 0 for no, 1 for yes. And we can do this easily just by looking at the first element in each block. If it's an edge, then this is spillover, otherwise it's not. And then we can align these vertically. So this is almost our denormalized table. However, there's edges of different adjacency lists in the same row. So we wish for each vertex's adjacency list to be in its own exclusive row, like this. And so to do this obliviously, we need to calculate the row and column for each element. Calculating columns is pretty easy since we can number elements in each block silently or non-interactively, and this gives the elements their column number. For rows, we need to use a different trick. So recall what prefix sum is. Given a vector x1 to xn, prefix sum computes a new vector y1 to yn, where each yi is the sum of the prefix of xi from 1 to I. Also observe that in MPC, prefix sum can be computed silently with additive secret sharings of all xi, so non-interactively. And we can use this if we take the prefix sum of our vertice and edge predicate. We can compute for each edge which vertex it belongs to, because it'll have the same label. And recall that we marked the spillover bits. So if we compute the prefix sum of the vertice and edge predicate and the spillover bits, we magically get the row number for each element. And so now each element knows both its row and column number. However, there are still some problems. We have all of this empty space, which reveals information, and there's potentially less than 2v rows. So we still need to create unique bots for each empty location, and we need to pad to 2v rows with bots as needed. And how do we do this obliviously? So rows can take many forms. A row can look like this with vertice edges in the beginning, and then we will pad with bots afterwards. Or it could start in the middle, and then we pad with bots around. Or this could even be a spillover block, where we need to pad with bots afterwards. Observe that in any event, all the edges are contiguous, and so we can mark both a first and a last edge. And the first edge will know exactly how many bots to the left of his column to fill, and the last edge will know exactly how many bots to the right of his column to fill. And first and last edges can recognize who they are just by looking at immediate neighbors. So this is pretty good, but if we just inserted bots before the first edge, we would reveal exactly where the first edge is. So we need to hide the number of bots inserted by first edge. And to do this, we create a separate row for each first edge and fill it completely with bots. In the beginning with real bots that have dedicated addresses, and for the rest of the row, we'll fill it with dummy bots. And every real address, a real bot knows its row and column, and every dummy bot needs to be garbage collected obliviously. So what is the situation so far? Our goal is to create this 2v by d table, where for each entry in this table, there will be a unique dedicated element created for each location. And we also have a bunch of dummy bots all over the place. And so how do we garbage collect all of these dummy bots obliviously? So here's the concatenated list of everything, and this is how we garbage collect. First, we'll shuffle everything. Then we'll disclose the locations of all dummy bots and erase them. And now we'll reveal all remaining addresses. Now, why is this secure? Well, recall first we shuffled, and there's a single dedicated item for each location in the table. So now, since addresses are in the clear, we can put every single item into its dedicated location, and every single row is edges all belonging to the same vertex. So everything is denormalized. Well, actually, this is not the full solution, as I didn't tell you how to fill the remaining empty rows. And for this, please see the paper. So to do this, we made the assumption that all the vertices are integers, 1 to v, but this may not always be the case. So assume we have a graph with arbitrary vertex names, where Zeus points to Poseidon, Athena, Hades, and so on. So how do we convert this to integers 1 to v? Well, we can start with the same trick, where we store this as one long list of 2 tuples consisting of Boolean vertex edge and then name. And we can pad these names all to be of the same length, and they all fit in a single word of RAM. And then we'll number each element. And the reason we do this is so that after we rename them, we can put all the elements back to their original spot, which they'll remember. And now we can use prefix sum again to silently give new vertex names to each vertex. So now Poseidon becomes 1, Hades becomes 3, and so on. Now our goal is to let all the Hadeses know that their new name is 3. So there's an edge Hades in Zeus's adjacency list, and there's an edge Hades in Poseidon's adjacency list. And they should be let know that their new name is 3. So how do we do this? First, we'll shuffle and sort by alphanumeric names, giving precedence to vertices. And what this will give us is a list of vertices followed by edges that point to this vertex or that have the same name. So we have Athena with all the edges that are also named Athena. And now we want to spread this new name of Athena to all of these edges and for all the other names as well. We can abstract this into a coloring game where we have an empty line that has no color. And on this line, there's n colors representing vertices. And we wish to spread these colors to the entire line or spread the name to all of the vertices, edges. So what are the rules of this game? Well, if we have a colored cell next to an empty cell, then we can color this empty cell. If we have 2 different colors, then we can't override the color or give some edge or vertice a name that it shouldn't have. And if there are 2 empty cells next to each other, then they should remain empty, unless we color them with a colored cell. And we can generalize these rules for any interval. So if we take any interval and we look at the 2 endpoints, if the leftmost element has a color and both of these endpoints have the same original name, then in one fell swoop, we can color this entire interval. However, if the 2 names on the endpoints are different, that means there exists another color in between them, and it's not safe to color this, and so nothing happens. So how do we color this entire line efficiently? So consider any interval, and for every I from 1 to log n, we'll execute simultaneously generalized rule on all intervals of size 2 to the I in parallel. So we'll consider places 1 and 2, 3 and 4, 5 and 6, and so on. And this may catch one empty cell and color it, or if it starts at the odd index, it may not catch it. And so to deal with this, we then do this in a brick pattern where we shift it over by half of 2 to the I before going on to the next I+1. And now we've definitely colored at least one uncolored cell for every single interval. And now we'll keep doing this in increasing powers of 2 until eventually the interval gets too large and will no longer affect the color. And at this point, half or less remain uncolored or not given the new name. And then, after finishing, we'll go down from log n down to 1, executing the same intervals of size 2 to the I in a brick pattern. So we'll do decreasing powers of 2, and eventually we'll get to the smallest size of just 2. And in the paper, we prove that after 4 log n plus 2 rounds, the line is fully colored. And so all the names are spread. And what does this mean? Well, remember the original positions? Now that we have the new names spread, we can shuffle and place into the original positions. And we have renamed the graph. So now Hades knows that his name is 3 in the adjacency list of Zeus and Poseidon. So unfortunately, I won't have time to cover oblivious priority queue and secure Dijkstra, but please see the paper for this. And in conclusion, first and foremost, We improved state of the art for secure Dijkstra using our denormalized replicated adjacency list. We showed an efficient oblivious conversion into such a representation and also an efficient oblivious graph renaming into the sorted integer representation. And this is potentially useful for other secure graph processing such as BFS and MST. Thank you.
Any questions from the audience?
So for dense graphs, the best solution was v squared in terms of work. And so we have v plus e log v. And so as the number of edges approaches v squared, obviously this becomes less efficient. But for sparse graphs, this is a significant improvement. And then for sparse graphs, the best solution before was v plus e log squared v, I believe. So we improved it by log v.
Any other questions? All right, let's thank the speaker again. Thank all the speakers of the technical event. There's a coffee break after this.